All right, so let me show you how to analyze the plate. So you just send me this file and I haven't touched anything so that you just identify what you sent to me. And what you can see here is that there are a lot of things that show background, right? So there's several ways of getting rid of that bad background. One is to go one by one and find where they are. Like, so if you just go one by one, see, it's in line G, and then you see this number 5 over here, you know that that is the bad well. So you can just one by one identify those wells, or you can go here on the left side where it says quality control summary, and you click there and it's going to tell you, okay, G2 has an issue. I1, I2, and I3 have an issue. G2 has an issue. So in this case, it says there's a lot of noise on G2, which is what we identified earlier. So what you can do is omit that well. So to get rid of that well, you right click with your mouse and you will see this menu, and then it will say omit. You can also do Control M, I think, for omit, and some computers that works, in others it doesn't. But when you do that, you will see that all of these things disappear now. And if you go back to the amplification plot, you no longer see some of the things that you saw before. So every time that you omit a well, you have to reanalyze the plate. And to do that, you have to click here on Analyze, and it will just take a little bit. And now, see the plot changed because we removed the high background looking well. So now we're going to go to the rest of the wells that show problem and see what kind of problem there is and whether we should remove or not that sample. So I'm going to go one by one, and usually you see the little triangle over here that I don't know if you see, it's like a yellow triangle. It shows up on top of all the ones that are problematic. So you can either go here to quality control and go to the wells, or you can go one by one and identify them yourself. I prefer to look at them one by one because sometimes the machine identifies an issue, but it's not an issue. It just says, oh yeah, there's this thing that's different, and you look at it and it's not. So let's just look at here. So here's your triplicates, right? So that you know, this is your first sample, sample 1. When you pipette it in triplicate, it basically looks exactly the same in the 3 wells, right? It's almost no difference. This is perfect pipetting. Congratulations. That's good on you, because that's you pipetting well, the reason that looks that way. Now the next one, we have 3, and what happened here is that this looks like a pipetting error. So this may be that you got some air in the tip, or maybe when you pipetted in that well, it didn't centrifuge well, it didn't go well to the bottom. Multiple things can happen. Sometimes there are just bubbles that are, in the master mix that has detergent, so you can't avoid that. So because this is gonna, you know that this is a technical issue because of the way it looks, and because it shows you here the triangle, we omit that. And the thing is, when you omit something, you can always go back and include it. So you still right click, and instead of omit, you click include, and it goes back. So if you are in doubt, you can always go back later and omit or include things. So every time that you change one of those, as I told you, you have to like reanalyze. And now we're gonna go here because this looks a little problematic. Okay, so here you go. So we have these 3 wells that look very different than each other. So let's just focus on the one in the center, right click, omit, reanalyze. Sometimes when you fix one, the other 2 get fixed. See, now the triangle of error went away because a problem was that the 3 wells were very different, but now we removed the problematic one, the other ones went away. So that is fixed. And let's just identify if there's anything else very obvious over here. This doesn't seem very weird. This is fine, see, it shows a triangle, but I don't know why. Here, same, it's okay. So I will not omit those wells. See, sometimes it's just this difference, but we only care about what happens here, so you don't have to worry about that. And you can always ask me. I have many years of experience doing this, and certainly I didn't learn everything in one day. All right, so here's another problem. See, the first well is okay, second well, the last well is okay, middle well, here you forgot to pipette it. So perfectly fine. So if we omit it, now we got rid of the problem. And now we have this one that, again, it shows like an error, but I think it's because of all of this that's happening here. So we don't care about that because it doesn't affect the result. All right, so I feel like I already looked at all of them and I cannot see anything problematic at a first glance. There's one thing that you didn't do, and because I didn't tell you, but the non-template control, we have to, let me just go here. We have to name the sample. So if I go here to define, I'm just going to name one sample, the non-template control, and then I'm going to assign it here to your controls. And that is so that we can visualize it. It really doesn't change the experiment if you do it or not. It's just easier when we export the stuff. So as I told you, when I explain you how to do this, you can always add and remove things, and the machine took all the information for all the wells. So now we analyze one more time to make sure that those template controls show up. And you see here these three numbers. Those are the thresholds. So that is the amount of fluorescence that is gonna meet the curve, right? So for example, in this case, this is the threshold, 0.97, and at the cycle where this sample met the threshold is at the 31 cycle, approximately, see, something between 30 and 32. That is called the cycle threshold, or the CT value, which is what we are going to report to the PI. However, the machine calculates this automatically using an algorithm that looks at the higher and the lower peak, and a lot of math in between. But what we found that is useful is to always have the same threshold for the same gene. And in order to do that, we look at the curves for the whole gene together, which I can do if I click on the full plate and select one gene, for example, RPLP0. And for me, usually it's 0.4 for everything. So if you just put 0.4 and you don't do automatic threshold and you leave the automatic baseline, then you reanalyze. And now every single time you run a plate, you put 0.4 there. It's more consistent across experiment. Now, let's do the same for the other gene. Let's try with 0.4. What you really want is that this is supposed to mimic like a C shape. You want it to be in the center of the C. So I usually try 0.4 first, and if it looks like it's awfully up or down, we reassess it. Otherwise, you can just go blindly and put 0.4 for all of them and see that it's still kind of in the middle. And you can do 0.5 if you want. Again, you can always change it. But as long as it's the same number for the same gene, for the same experiment, it's good. If you keep changing it up and down, then you're not going to be able to compare one sample against another. So now that I normalize the threshold, I analyze one more time, and now everything looks a little bit more consistent, right? So now I am able to compare at which cycle each of the samples met the threshold. So for example, for the housekeeping control, you can see here two populations of genes. The pink one and the blue one, I assume those are the liver and the testes. And you see a little bit of pink over here. This is probably the non-template control. Or it may be some sample that just expresses less or has less amount. I don't know. We will have to analyze the data later. Now for the NAE1, you see a lot of samples with similar CT, and these ones have way more variability. This is probably their treatment. It's just different in the two subsets of samples. And they're probably, this is one tissue and this is different tissue. And now for the CAR7, same. You can see the two tissues and a little bit of variability among them. So to do the analysis, we are going to need the CT value for the gene, in this case CAR7, or NA1, and the city value of the housekeeping, because we're going to use a formula that incorporates all those values and does a mathematical calculation for the gene expression. So now how do we get that out? We go to export here, and you see here everything in a tabular form. And you don't need everything here. What you do need here is only what is in the results tab. So as you can see, I unclick everything else because I don't want it. I only want the results table. The results table is going to tell me which well, what sample, what target, and what is the CT value, which is what you want. So the only thing that I am going to tell you to remember to do here is to unclick this. This says skip the omitted wells. What you did in the prior step is you remove those wells that had crazy amplification plots. So when you don't skip this, when you skip this, then what happens is it puts it all together. When you remove it, it leaves the empty space. So I don't know if you can see here what happens around here. Concentrate here, for example, in A4. See how it just goes away and comes back. So now I want this space because I want to be able to tell the PI that I omitted that well. Otherwise, it just gets rid of it and you are not going to remember what happened. So once you selected what you want to export, you select how you want to export it. And here's several options. You can select to do it in Excel, or you can select to do it as a text file. Unfortunately, the machine that is there in the core facility probably will not let you do the Excel because there's no Excel in the computer. So either or is fine. You just export it as a text if you want, and then you import it from Excel, or try to export it as an Excel file. Either format, you just click on Start Export, and then it just exports it for you. So in this case, it's going to open it as Excel, but I'll show you how it looks like when you export it as a text. All right, so here's how it looks as Excel. It's going to tell you what you ran, when you ran it, the different calibrations. See, these are all the calibrations I did. This is the experiment. When was it run, the number of instrument, what was the passive reference, and your protocol too, just in case you have to go back at any time. And then here it tells you, the well position, with the sample, and the CT value. So I can explain in another video how to do the analysis, but what I agreed with the PI is that we were just going to send them the CT value. So what you're going to report to them is this Excel file, or you can just create a table with the sample, target gene, and the CT only, and everything else you can get rid of because it's not important. All right, so this is how it looks like as Excel, and this is how it looks like as text. And the one thing that you need to remember is that when you're going to export, you have to tell the computer where do you want to save this. You can go here and select the desktop if it's easier, because otherwise it just goes in a folder there in the computer that you may not be able to find later. And here you can change the name of the file. All right, I think that's it. But once you are done doing all the other probes, we can talk about how to put together all the results. And there is a software online that we can use to provide analysis for them. Or we can just send them the CT value. I can email the PI and let them know that we offer those two options. Because if we want to do the full analysis for them, we need to know which sample is going to be their control. We need a calibrator control. So the formula doesn't work without a calibrator. Everything is relative to that one sample. And usually you want to choose that sample as the control of the experiment, but we don't know anything about their experiment. So we can have that conversation with them now that we know that the PCR worked. But I hope this was helpful.